Hi everyone, welcome to this talk. My name is John. I'm an open source engineer at Hackages, and during the next 25 minutes we are going to talk about the web. In my opinion, the web is an amazing platform. And I think that we can all agree on one fact, is that the web has evolved a lot since its beginning. We went from sending simple text over the wire to providing a full experience to the end user. And I think one key component within the web that has brought this experience is JavaScript, right? So JavaScript, built in 1985, shipped within the Netscape browser, was aiming to provide some dynamism to the static content of the web. But what we were trying to achieve with JavaScript at that time, it's a much smaller part of what we are doing with it now. So the way that it was executed at that time is quite different from the way it is executed nowadays. So at that time, JavaScript was interpreted, okay? And to take a closer look at what interpretation is, for example, here we have in the middle our interpreter, JavaScript interpreter, okay? And on the right side, we have kind of like the bare metal machine, the CPU. On the left, we have a bunch of JavaScript code lines calling add functions, passing numbers. And when the execution hits the first line, the line is sent to the interpreter. The interpreter does his job, okay? Evaluates both parameters, their type, what we are trying to achieve, and then outputs some machine code that gets directly executed by the CPU. Next line, same process, again. Evaluating both parameters, saying what kind of types they are, and then outputting some machine code. And the thing here that this mechanism worked until kind of 2005, when big JavaScript apps started to come onto the scene. And one example is Google Maps, which browser started to hit kind of like a performance issue with those JavaScript apps. And why? Because at the end, doing a simple addition in JavaScript is not trivial. You have to check both operands types, and regarding regarding the evaluation, you will output some different code. So you cannot really count on the language by itself. You have to wait until runtime. So one of the mechanisms that browsers applied to solve this issue, it's a very well-known mechanism, which is called just-in-time compilation. And if we take back the same example, we still have both items there, but you have a third component within the system, which is the just-in-time compiler, okay? We take again the same lines. First line is sent to the interpreter. It does the same, evaluates, interprets it, outputs some machine code, and that's it. Second line, same process. Evaluate it, both parameters, and then output some machine code. But this time, the interpreter has monitored the code and the execution, and it has some feedback about the execution. So it can see that, okay, we tried to execute twice the same function, passing twice numbers. So it marks that function as hot, and then pass it to the just-in-time compiler to compile it and output the same machine code that it was previously outputted, store it somewhere in memory, and lock that memory region so we cannot override it. Third line comes to execute it. And then there, the interpreter says, okay, I know this add function. It's not the first time. I just asked the just-in-time compiler to compile it and put it somewhere in memory. So are still both parameters numbers? Yes. Okay, you can then take the one that I just compiled it and directly execute it. And if you see this here, what we have done, what the engine have done is just that he made a shortcut for the execution of a function. And we call that a fast path, okay? And that's when JavaScript gave us his top speed. And just to show you the difference between non-jitted code, so non-jitted JavaScript and jitted JavaScript, I just launched an instance of Chrome disabling the optimization of JavaScript. And you can see for 8 robot dancer, it's kind of laggy on the left side, but on the right side, it's kind of going very well. You can even, I think I increase until 15 and it's still okay. But then, well, we had the performance issue with JavaScript, with interpretation. We compile it and it works pretty well. Why do we want to go further? Well, the thing is that I didn't tell you the whole story. If we go back to example, and this time I'm sending, instead of 2 numbers, 1 string and 1 number, the interpreter will try again to say, okay, I know this function. I just store it somewhere. But are still those 2 parameters numbers? Nope. So what he's doing is that he is going to fall back to interpretation and erase the compiled version that he had. Yeah, super animation. So at the end, what's the problem with JavaScript? Well, I mean, not the problem. I don't want to offend you. I'm sorry. I'm sorry. Then what's the thing? What JavaScript is lacking to be optimized before execution? Well, JavaScript is just lacking predictability. If you take the same version, I mean, 2 versions of the same code, one written in C and another in JavaScript, you can clearly see that in C, the language provides some hints to the compiler so he can optimize code before runtime. If you look at the JavaScript side, there's not much going on there. Even the number of parameters are not really fixed, so you can pass more than 2 if you want. So if we quickly recap what we learned here, or no, maybe what we have to. So we can optimize JavaScript, and it's cool. And you can have really good performance with it. It's not a problem. But the thing is that JavaScript is not predictable. So the industry, browsers, have tried to solve this problem. To fix this. And they try to run some more predictable code within the browser. And one of the initiatives is, for example, portable native clients from Google, which was to run some C++ modules within the browsers, sandbox it, so it's secured. But it didn't really took off. After that, Mozilla came with an idea of just taking a subset of JavaScript, which was more predictable, and they call it ASM.js, but it wasn't enough because it was still JavaScript at the end. And in 2015, browsers reunited and tried to come up with something that they could agree on to go a step further, to push the limit of the webs. And that's where WebAssembly came onto the scene. And what is WebAssembly? If we take quickly just the text from the official page, which is quite dense, I'm going to read it. So WebAssembly, abbreviated WASM, is a binary instruction format for a stack-based virtual machine. WASM is designed as a portable target for compilation of high-level languages like C, C++, Rust, enabling deployment on the web for client and server application. A lot of things, huh? We are going to try to read it again, but step by step. So WebAssembly, abbreviated WASM, is a binary instruction format. So it just means that it's a set of instructions encoded in a binary way. So it's quite efficient to load it. Designed as a portable target for compilation. So 2 things here. Portable, it means that WebAssembly is not just designed for the web, but it's also designed to run outside the web on other platforms. And target for compilation means that you don't have necessarily to write WebAssembly. It's quite low level. You're more likely to write in higher level languages like C, C++, Rust, Go, C#, Java, whatever, and you compile to WebAssembly. So how the process goes? Simply, you take a bunch of files, C, C++, here, I mentioned just C and C++. You compile it to an intermediate representation. It's almost always LLVM. I will skip the details about LLVM, okay? But normally this part is quite hidden from the developer perspective, okay? And then you compile as a backend compilation to a simple .wasm, in this case is the name, but a WASM module, okay? And with which tool, for example, one of the main tools to compile to WebAssembly is Emscripten, which mainly mission, is to bring other languages on the web. So then how do you consume this simple .wasm? Well, you fetch the resource. I think you all know this. You fetch the resource, and then you just call the JavaScript API, WebAssembly APIs that are nowadays available in all the browsers, the major browsers, and then you receive a WASM module which you can call function on it. Here, exported function. And those functions were originally written in another language. So what are the goals of WebAssembly? WebAssembly wants to be performant, run at nearly native speed. After that, WebAssembly wants to be portable, okay? So not only running on the web, but also running in other platforms. And secure by default. It's one of the main concerns of WebAssembly, being more secure than JavaScript. Performance. Well, I might disappoint you, but JavaScript is not, WebAssembly is not so much faster, more faster than super optimized compiled JavaScript. At the end, they quite run nearly at native speed. But the thing is that WebAssembly will more likely to stay on the fast path when you have an optimized version of it, while JavaScript will kind of de-optimize easily and falls back to interpretation. And to illustrate my point, here you have just a diagram showing multiple execution of the same code in JavaScript and then the same code in WebAssembly in blue. WebAssembly is faster, okay, but the point here is to show that for multiple execution of the same code in JavaScript, you cannot predict the performance, while in WebAssembly it's almost the same. Also, WASM can be decoded, validated, and compiled in a fast single pass, equally with either just-in-time or ahead-of-time compilation. If you check how JavaScript is handled within a browser, you first fetch the whole resource, and then you parse it, compile it, and execute it. All that in the main thread. There are some exceptions, okay? Not everything happens sometimes in the main thread, but that's kind of the regular way of doing it. But browsers handle WebAssembly in another way. So while fetching the packets, while fetching the resource, the WASM modules, the browser will directly compile the bytes that are on the fly. And when it's done, it will execute on the main thread. And the compilation doesn't happen on the main thread, so it does not block users. Just to show you the difference of performance, you have 30 robot dancer here, and you can see that in JavaScript it's quite laggy. When you switch the execution to WebAssembly, it goes back to normal. And you can even increase the number, and I'll go there until, I think, 120. But you will not see the difference because the screen is too short. Yeah. Okay, so portable. At the beginning, WASM was meant, the first version of WASM, it was meant to at least work on the browser. So the way of execute WASM was to provide some GS glue code that when a WASM module was trying to do something that the browser couldn't handle, at least the JavaScript will handle the code and emulate something. For example, calling a file system. You cannot call a file system within the browser. So when folks tried to run WASM outside of the browser, what they tried to do is just to run the existing WASM module outside the browser. And so they were kind of emulating GS glue code that was emulating a system interface. So it's not really the most optimized way to do it. So a need of, as much as WASM is a language for a conceptual virtual machine, it needed a system interface, a standardized system interface for a conceptual operating system. That's when WebAssembly system interface came onto the scene. It's just a specification that that WebAssembly modules can call to make some system APIs call. Kind of, it's just an operating system. It's not, let's say it's kind of like a POSIX way of doing, okay? So then the diagram becomes like that. You have the non-browser or browser runtime that implement WASI and expose some system interface API that WASI modules can interact with. I wanted to show you one tweet of Solomon Hykes, which is the founder of Docker, that is saying that if WASM plus WASI existed in 2008, we wouldn't have needed to create Docker. That's how important it is. It is WebAssembly on the server is the future of computing. A standardized system interface was the missing link. Let's hope WASI is up to the task. Also, folks from Clever Cloud, a French company that is, I think, here, maybe you have met them, are running function as a service in WebAssembly directly on the hypervisor. So no operating system between the code and the hardware. Okay, WebAssembly wants to be secure by default. Nowadays, when you code, it's the result set of binaries is just 20% your code and 80% dependencies that you haven't written. Then what happened is that the way that we execute programs nowadays is just they execute within the ambient authority. So me as an admin of my machine, I'm going to ask my program to run, and then I'm going to provide him my whole set of keys, the permissions that he can run. Maybe he doesn't need it, but it's okay. I just wrote the code, so I know it will not do some malicious things. The problem is that it also passed the whole set of keys to its dependencies, okay? And sometimes you have a malicious dependency, okay? So that malicious dependency can then use all the rights that you provide to execute some malicious code. WebAssembly wants to execute itself as capability-based systems. So it means that I still have this whole set of keys, but when I'm going to run the whole program, I'm not going to pass all the permissions. I'm just going to pass the permissions that I think my program needs to perform his task, okay? So I'm just passing here kind of one key, and then this key is passed to all the other dependencies. But this time, the malicious code is quite blocked and cannot really perform the malicious task. Also, one abstraction that WebAssembly wants to provide is called nanoprocesses. So the idea here is to execute competing modules, WASM modules, in the same process. So kind of the result is kind of like that. So you have the whole process, which is like the big box, blue box, and then inside you will have like the first one is like your main module, the one that you have written, and it has dependencies to other modules, but they all run within kind of in a sandboxed way, and they think that they are alone within the memory space, the process. It's just a software fault isolation. So why WASM wants to be secure? Because first, it provides capability-based systems. Also, it's sandboxed by default, okay? So you can run low-level code in a secured way. And also, nanoprocesses provide a way to communicate between different modules a lot much faster than inter-process communication, okay? And the end result is kind of like that. So you write your main module in, for example, Rust, and then you consume some dependencies that were originally written in other languages, like C++, Go, and so on. I mean, there are not only these languages, huh? There are a lot of more, but voilà. So, projects. I just took 2 examples. There are a lot, okay, but you can check. As you are all JavaScript developers, I wanted to show you AssemblyScript, which is just, it's a subset of TypeScript that does not compile to JavaScript or transpile to JavaScript, but compiles directly to WASM modules and WebAssemblies, okay? And because I'm a .NET guy, I wanted to show you, I'm also a .NET guy, I wanted to show you that you can run now the CLR, so the .NET, on the browser through WebAssembly. And they provide now kind of a framework which is quite similar of like Angular to write front-end applications in C#. Go check this link, it's really interesting. There are a lot of things, and that guy, Embasso, I think he's Italian, and he's doing a C++ front-end library to write front-end application that compiles to WebAssembly, and it has also provided kind of like GS6 syntax for C++. It's super interesting. The bytecode alliance. So big companies reunited and tried to push WebAssembly and a secured by default web. And they call themselves Bytecode Alliance. These are the four founders of the Alliance. And you see pretty big names. And just to tell you, Fastly is running 10% of the internet. And I will end up my talk with one quote that I think it's kind of resume what I feel about WebAssembly, is that WebAssembly is the first fast multi-language retargetable and safe intermediate representation that we have ever agreed upon as a community. CTO of Fastly. Voilà. Thank you. Okay. Any questions?
I have a question about Node.js. So in Node.js,
yes.
You can run native C++
yes,
modules,
of course,
and
yeah.
you can run WASM.
Mm-hmm.
What do you think is better to run in Node.js, WASM or C++, and why?
It's a question that a lot of folks are asking. To be honest, I think that for now it's C++ that will continue to be like the major solution to provide native performance within Node modules. But at the end, it will switch to WebAssembly modules because I don't know. In my humble opinion, I think it's kind of like the future of the industry, or in this perspective. But they both solve your issues, which is giving you performance, and so on.
Hi. WebAssembly is a fairly young language. Do you have an overview of the tools and debugging tools around it? Because as it's a binary format, I guess it's a little bit harder to debug than, let's say, vanilla JavaScript.
Yes. Okay, so there are already, I think, some browsers that provide debugging tools to work with WebAssembly modules. You have, I think, within Mozilla Firefox, you can already kind of work with it and debug. The thing is that I didn't mention, and you're right, WebAssembly has two representations. It has the one that browsers use to execute it, which is the binary format, because it's load efficient and so on. But for human readable, it's not the most human readable format. So they also have a text representation, which is WebAssembly text, I think, what, or something. It's called what. And then you can really clearly see that it's low level, kind of like an assembly code.
I have a question about the micro frontend and how WebAssembly will do in this architecture. So
Assembly.
Yeah, WebAssembly.
WebAssembly will do in which architecture?
In the micro frontend.
The micro frontend architecture.
Yeah.
Okay. WebAssembly are quite. I mean, it's composed of several modules. So if your concern is to say, do I have to download the whole module, big module to execute it? No, you can kind of split it, and in the future you will be able to lazy load it. So yeah, I think you can already do that now. To be honest, because at the end, as you saw, I mean, you're just fetching a resource on the internet, and then you can fetch it whenever you want. If it's sorry.
Can I run Blazor beside Angular, both in one
Yes, I will say yes, yes. There is no, really, they're not competing. I mean, if they're loaded into your browser, you can run it on both sides. But maybe you will struggle a bit to make them work together, but I think it's completely feasible, of course.
Okay. Is WebAssembly able to access to the GPU?
Okay, so this talk that I've done, it's normally much larger, and I covered all the topics. One thing that, so your question is it possible to call some GPU APIs from the WebAssembly? Right now, no, because the only thing that provides that is standardized is WASI, which is kind of like a system interface to call some the OS APIs. The thing is that WASI wants to extend itself, and so you, in the future, you would be able to call some specific domain-specific low-level APIs, kind, for example, GPUs, okay? Or you will be able to call, I don't know, something related to blockchain or whatever. So go check WASI, go check on the internet WASI. It's really, they really want to extend themselves, and they're open to feedback from the community.
Thank you so much.
Thank you. I'm Edward.
So if you don't, he might be available just outside for questions.
Yes.
So the exit, look.